Hello guys, good evening. I welcome you to today's experience. The course is still renal physiology by me. I'm streaming live from Lagos City in Rivers State, Nigeria. Yep. Okay. In module 1, we discussed about the microscopic structure of the kidney. In today's module, we were looking at the physiologic roles of the human kidney, the functions of your kidney. Yes, that's what we'll be looking at in today's lecture. Firstly, we are going to introduce today's lecture, and then we'll discuss the homeostatic roles of the kidney. We'll now discuss the endocrine or hormonal functions of the human kidneys, and then we'll look at the excretory functions of the kidney. Please get your writing materials and make sure you make notes while this class is going on. Thank you. Alright. It is easy to think of the kidney as a mere excretory organ, but they are much more complex than that. You know, if you were asked, state the functions of the kidney, I believe you'll say excretion. Fantastic. But the kidney has other roles besides the excretion of metabolic waste products. We are going to look at all of that in today's lecture. Generally, the human kidney plays a vital role in the elimination of metabolic waste products and in maintaining the body's homeostasis or the status quo ante. Alright, these are the two basic roles of the human kidneys. Now, to make things easy, I'm going to categorize the functions of the human kidneys into three. The first part is the homeostatic functions of the kidney, and then we'll look at the endocrine functions of the kidney, and then finally we'll look at the excretory functions of the kidney. All right. Okay. The homeostatic roles of the kidney. The kidney controls fluid balance, plasma osmolarity. It also regulates pH or acid-base balance, and it also controls BP. We're going to look at them one after the other, beginning with regulation or control of fluid balance. Okay, now water gets into the body through fluid intake. Yes, when you take fluid, you are actually ingesting water or taking in water into your body. So one of the primary ways through which water enters the body is by drinking it. Okay, so fluid intake. Another way water gets into the body is by ingesting food, eating food, and then by food metabolism. In the same way, water leaves the body through urine, and then by sweating, that is insensible loss of water, and then by respiration through the lungs, and feces. When you go to the components to poo-poo, you are also excreting some parts of water. Alright, so these are the major ways through which water goes in and out of the human body. Going forward, now fluid is said to be balanced when fluid intake is equal to fluid output. Now, if fluid intake exceeds fluid output, it is known clinically as edema. It means there is excess water in the body than solutes, and the patient begins to swell. And if care is not taken, if that patient is not attended to medically and immediately, he or she could just swell and burst. It's a serious clinical condition. Alright, edema. Good. When fluid intake is less than fluid output, a clinical condition known as dehydration. Dehydration is another clinical condition. When the body is lacking fluid, that is, fluid intake is less than fluid output. You are passing out more fluid than taking in fluid. Alright? So when this happens, your cells and tissues becomes dehydrated. They start lacking water. and dehydration could lead to low ECF volume and low blood pressure, and then if care is not taken, you could even die of hypotension. Hypotension is a very serious clinical challenge, and even hypertension. We are going to look at all of this as we proceed. The kidney controls fluid balance by conserving water when it is low in the body. Another way the kidney controls fluid balance is by excreting water when it is excess in your body. Alright? It does this through a mechanism known as the renin-vasopressin test mechanism. This is how the kidney helps you and I to regulate of fluid balance when it is in shortage. Alright? Not only that, the test center is also activated. Test center is located in the brain. Alright? When you lack water, the test center is stimulated, causing you to drink more water. By taking in more fluid, the low water content in the body is reversed to normal. So this mechanism, the renin-vasopressin test mechanism, is a mechanism the kidney uses to control fluid balance. Alright? Going forward, the next thing is the regulation of plasma osmolarity. The kidney also helps us to regulate electrolytes, especially sodium ions, in the body. Alright? The plasma osmolarity is the amount of solutes in the blood. The major determinant of plasma osmolarity is sodium ion. Sodium ion, please take note of this. Sodium ion is the major determinant of plasma osmolarity, not hydrogen ion or potassium ion or calcium, but what? Sodium ion. Okay, the normal range of plasma osmolarity is 290 to 300 milliosmol per liter. When plasma osmolarity falls below 290 milliosmoles per liter, what happens? The body is in a state of hypoosmolarity. It means that you will have less solutes in excess of water. In the same way, when plasma osmolarity becomes greater than 300 milliosmol per liter, it leads to a condition known as hyperosmolarity. It means there is excess of sodium ions in the blood, which would need to be, of course, excreted. Alright? Now, the human kidneys regulate plasma osmolarity by a mechanism known as the renin-aldosterone system. Alright? When there is hypoosmolarity, the kidney is again activated, leading to the secretion of renin. Renin acts on the adrenal gland. The adrenal gland is made up of two parts. We have the adrenal cortex and we have the adrenal medulla. In this case, the kidneys renin will stimulate the adrenal cortex, leading to the secretion of aldosterone. When aldosterone is secreted, it again enters into the blood and then goes straight to the collecting ducts of the kidney. When this hormone is acting on the collecting ducts, it leads to conservation of sodium ion. So it inhibits the excretion of sodium ion. When this happens, the low sodium ion in the blood, or the hypoosmolarity, is immediately reversed back to normal. Conversely, when there is hyperosmolarity, this renin-aldosterone mechanism is immediately inhibited. So renin is not secreted by the kidney because the sodium ions in the blood as at that time is in excess. So if renin is not secreted, the secretion of aldosterone is also inhibited. So there is no conservation of sodium ions. Instead, there will be excretion of the excess sodium ion, which will now return the excess sodium ion in the blood to normal. Alright? Good. Regulation of pH. pH simply means acid balance. Okay? It is the degree or amount of acidity or basicity in the blood. The major determinant of pH is hydrogen ion. Hydrogen ion. Okay? Hydrogen ion. This is the major determinant of pH. When hydrogen ion in the blood increases, it simply means your blood is acidic. But when it decreases, it means your blood is basic. Alright? So the normal hydrogen ion range in the blood is between 7.0 to 7.4. Okay? This is neutral per se. When the hydrogen ion content in the blood decreases below 7.0, then the body is in a state of or is in a condition known as acidosis. Conversely, when it increases above 7.4, the body is in a state of alkalosis. Okay, it simply means there is a problem. Going forward, the human kidney regulates pH or acid-base balance through a mechanism known as renin-aldosterone bicarbonate mechanism. When the hydrogen content of the blood is in excess, this system becomes activated. Alright? The kidney secretes renin. Renin again activates the adrenal cortex, leading to the secretion of aldosterone. Aldosterone enters the blood, goes to the nephron, causing the excretion of the excess hydrogen ion. So you pass out more hydrogen ions in the urine. Okay? This will eventually help to return the excess hydrogen ions in the blood to normal. Okay? In the same way, the bicarbonate system is activated. Remember, bicarbonate is a buffer. Alright? It helps to bind excess hydrogen ions in the blood. So during acidosis, the bicarbonate system binds with hydrogen ion. Bicarbonate ion binds hydrogen ion, forming carbonic acid. Carbonic acid is not a stable compound. It will eventually dissociate into water and carbon dioxide, which are not toxic. In this way, the renin-aldosterone bicarbonate mechanism helps to control pH of the blood. Conversely, when there is less hydrogen ion in the blood, in alkalosis, this mechanism is inhibited. So renin is not secreted, aldosterone is not secreted, bicarbonate ion is not activated, and then more hydrogen ion is being conserved by the kidney. Alright? When this happens, this low blood or plasma hydrogen ion is reversed to normal. This is how the kidney helps us to control or balance pH. Alright? Okay? Going forward, regulation of blood pressure. Blood pressure is the force exerted by the blood on the walls of the vessels. The normal blood pressure in a healthy adult is around 120 over 180 millimeters of mercury. Okay, that's in a healthy adult. This value could change as a result of age, disease, exercise, and so on and so forth. I'm going to teach you all of that in cardiovascular physiology. Now, when blood pressure falls below the normal range, a condition known as hypotension occurs. Hypotension is a very deadly disease. It is even more serious than hypertension. Okay? But when blood pressure increases rather above normal, a condition known as hypertension occurs. Okay? The human kidney regulates blood pressure through a mechanism known as the renin-angiotensin-aldosterone system. Okay? When BP falls below normal, again, renin is secreted by the kidney, leading to the secretion of the activation of angiotensinogen to angiotensin 1 and then to angiotensin 2. Angiotensin 2 will therefore activate aldosterone from the adrenal cortex. Aldosterone activation would therefore lead to the retention of salt and water. This would eventually return the low BP to normal. Again, when BP rises above normal, this mechanism is inhibited, okay, leading to the excretion of sodium ions and water, and then the return of the high BP to normal. I hope that is clear. Okay, I can hear someone say yes sir. Going forward, endocrine functions of the kidney. The human kidney produces 3 hormones. The first one is known as renin. Of course, I've been talking about renin ever since I started this lecture. Okay, the second hormone secreted by the kidney is erythropoietin. And the last one is 1,25-dihydroxycholecalciferol. These 3 hormones are secreted by the human kidney. Okay, and they have their specific and different functions. Let me show you. Now, we'll start by the renin-angiotensin-aldosterone system. This mechanism or system is something you must see in your exam. You cannot escape it in medical school. The renin-angiotensin-aldosterone system. You will meet it in renal physiology. You will meet it in endocrine physiology. We're also going to meet it in cardiovascular physiology. So every now and then you'll be asked questions on the renin-angiotensin-aldosterone system. So I'll urge you to pay attention. Thank you. Alright, going forward. The stimulus for the secretion of renin-angiotensin-aldosterone system, also known as the RAS, is 1. Hypotension, when there is low blood pressure. Okay. 2 is hypovolemia. This simply means low ECF volume. 3 is hypoosmolarity, that is low sodium ion in the blood. Okay. The next one is hemorrhage. Hemorrhage simply means excessive bleeding. And the other one is dehydration, that is low water content in the body. And then we have low renal perfusion, that is when the kidney is not getting enough blood. Okay, these are the major stimulus that leads to the secretion of renin-angiotensin-aldosterone system, basically renin. Okay, now these stimulus activate the juxtaglomerular cells of the kidney to release renin. Alright, how does this work? Now, decreased renal perfusion or hypotension or hypoosmolarity or dehydration would stimulate the kidney. Stimulation of the kidney would lead to the secretion of renin. This is renin being secreted by the kidney. Renin would then convert angiotensinogen secreted by the liver into angiotensin 1. Angiotensinogen is an inactive compound. It is synthesized and secreted by the liver. This compound is converted by renin to angiotensin 1. Angiotensin 1 is further converted. Let me cycle this. Okay. Angiotensin 1 is further converted into angiotensin 2 by an enzyme known as angiotensin converting enzyme, secreted by the lungs. Yes, your lungs. Alright, let me take it again. Decreased renal perfusion will lead to secretion of renin. Renin will act on angiotensinogen, which is secreted by the liver, to converting it to angiotensin 1. Angiotensin 1 is further converted to angiotensin 2 by angiotensin converting enzyme, also known as ACE. Now, angiotensin 2 has so many functions in the human body. Okay, the first thing angiotensin 2 does is to act on the pituitary gland, the posterior pituitary gland, leading to the secretion of vasopressin. This is ADH. ADH is also known as vasopressin. The secretion of vasopressin from posterior pituitary gland would act on the collecting ducts, leading to retention of water. Yes, you heard me right. That is what it does. Okay, the next thing the angiotensin 2 does is to act on the blood vessels. It leads to vasoconstriction of vessels. Okay, angiotensin 2 is known clinically as a potent vasoconstrictor agent. So when blood vessels are constricted by this compound, it will lead to an increase in venous return, and then when venous return is increased, the ECF volume is increased. When this happens, that is, increase in ECF volume will further leads to an increase in systolic blood pressure and diastolic blood pressure, thereby leading to an increase in BP. Alright, the next action of angiotensin 2 is to stimulate the adrenal cortex. Adrenal cortex. Stimulation of adrenal cortex would lead to the secretion of aldosterone. Remember aldosterone? Yeah. This hormone acts on the collecting ducts of the kidney, which will further lead to retention of sodium ions. When sodium ions are retained, water is also followed, is also conserved. So the retention of sodium ion or reabsorption of sodium ions is further followed by water. Is immediately followed by water. Alright? Okay, going forward, the next action of angiotensin 2 is to act on the adrenal medulla. The adrenal medulla secretes catecholamines. That is the epinephrine and the norepinephrine. The catecholamines immediately provoke the activation of sympathetic nervous system. Alright? This stimulation of the sympathetic nervous system would add to the vasoconstriction of blood vessels. When the blood vessels are constricted, again, it will lead to increase in venous return and an increase in ECF volume, which will further increase the low BP to status quo. Beautiful. Going forward, I have explained the actions of angiotensin in this slide. So on the slide, angiotensin 1 plays a vital role in the synthesis or the generation of angiotensin 2. So it is a precursor of angiotensin 2. It does not have any other role apart from acting as a precursor of angiotensin 2. Angiotensin 2 has the following roles. 1. On the blood vessels. It is a potent vasoconstrictor agent, as I earlier mentioned. 2. On the pituitary gland, it leads to the secretion of vasopressin or ADH, that is antidiuretic hormone, and the adrenocorticotropic hormone from the anterior pituitary gland. 3. It acts on the adrenal cortex, leading to the secretion of aldosterone. 4. It acts on the adrenal medulla, which eventually leads to the secretion of catecholamines. 5. It acts on the brain, which stimulates the test centers. When the test centers are stimulated, it leads to increase in fluid intake. Alright? Good. Angiotensin 3 has 100% aldosterone secretion and 40% pressor activity. When I say pressor activity, we are talking of constriction of blood vessels. So this angiotensin 3, its function is to cause secretion of aldosterone, and also it also causes vasoconstriction of blood vessels. So on the slide, you can see that there are 3 types of angiotensins. We have angiotensin 1, angiotensin 2, and angiotensin 3. And these three compounds have their various physiologic roles in the body. So you must note all of that. Going forward, note that angiotensin 2 acts on the distal convoluted tubule of the nephron. Okay? We are looking at the hormones acting on the nephron. Angiotensin 2, that is this hormone here, acts on the distal convoluted tube of the nephron. ADH and aldosterone primarily acts on the collecting ducts, leading to retention of water and sodium ions. Erythropoietin. About 85% of erythropoietin is secreted by the kidney. So you could see how important the human kidney is. While 50% of this hormone is secreted by the liver. Wow. The kidney is very, very important, and it contributes in the production of red blood cells. The red blood cell is the cell that carries the oxygen pigment. Okay, very important. So that is why sometimes when a patient has renal failure or kidney disease, it is very difficult to manage such a patient, because the patient will automatically become anemic. The blood cells production is compromised. So it's a serious problem sometimes when you have kidney failure. It is difficult. In fact, it is very rare that you survive, even with all the millions you have in the bank account. Okay, so that it is very important that we protect and take very good care of the kidney. It's funny how some guys go to Malaysia to sell their kidney. This is bad, just because of money. How much would you make by selling your kidney? You may not even live to enjoy that money after doing that. Okay, so the kidney produces 85% of erythropoietin, and only 15% is produced by the liver. Hypoxia is known to be the primary stimulus for erythropoietin secretion, followed by hemorrhage, excessive bleeding or loss of blood, which stimulates the kidneys to secrete EPO, that is erythropoietin. Functions of erythropoietin: it enhances hemoglobin synthesis. It also produces red blood cells from the bone marrow. Okay, note that in renal disease, the liver cannot compensate for EPO deficiency, hence anemia develops. I have said that earlier in this class. When the kidney is damaged, it's a very serious health challenge that could even lead to death, even with proper management, even with good medical care, even if flown abroad to manage the problem, it could still lead to death. Alright, we shall talk more on that in subsequent lectures. Okay, the next endocrine function of the kidney is the secretion of 1,25-dihydroxycholecalciferol. The normal calcium range in the blood is 10 mg per dl. Okay, that is a normal physiologic range of calcium ions in the blood. When calcium ion decreases below 10 mg per dl, hypocalcemia develops. Again, when it increases above 10 mg per dl, hypercalcemia develops. These are serious clinical conditions. Remember, calcium has so many roles in the body. It helps in mobility, that is the contraction of muscles, which leads to movement and locomotion from one place to the other. It also helps in the contraction of the heart. It is a reason for prolonged prolonged action potential of the heart, plateau. Okay, all right, amongst other roles. Okay, 1,25-dihydroxycholecalciferol is a steroid hormone formed from vitamin D. It is necessary for calcium homeostasis, or bone mineralization, if you like. In hypocalcemia, the kidney secretes 1,25-dihydroxycholecalciferol, leading to absorption of calcium ions from the gut, GIT, the intestine in particular, and the reabsorption of calcium ions from the collecting ducts. It also leads to production of osteoblast cells. Osteoblast cells favors calcium ion release into the blood. Okay, these processes would eventually or ultimately elevate the low plasma calcium ions to normal. All right, so this is how the kidney regulates plasma calcium ions in the body. When it falls very low, it is automatically activated, leading to the secretion of this hormone. This hormone will eventually lead to absorption of calcium ions in the GIT and reabsorption. That is, instead of losing calcium ions in the urine, they are retained in the body. All right, and then it helps to produce or stimulate the synthesis of osteoblast cells, which will eventually return the low blood calcium ion levels to normal. Hope that is taken. All right. Now, finally, we'll look at the excretory functions of the kidney. The kidney excretes metabolic waste products which are no longer needed by your body. Okay, examples of these metabolic products include urea, which is derived from protein metabolism. We have creatinine, which is derived from muscle metabolism. Uric acid derived from nucleic acid metabolism. Bilirubin derived from hemoglobin metabolism, that is the production of hemoglobin. And then it also excretes other drugs and chemical metabolites ingested into the body. These waste products should be eliminated from the body as rapidly as they are generated. But it's important that whenever you are pressed, whenever you have the urge to urinate, immediately rush to the convenience to do so. It is very bad to accumulate waste products in the body. It could lead to some serious health challenge. Alright, so don't tell me you're Superman or Superwoman or you know how to hold your urinary physics. Please, rush. Take excuse, even if you're in class, you're in church. Take excuse and immediately rush. Visit the nearest convenience and pass out the urine or the physics. Do not wait a sec. Alright? Up next is urine formation. Urine formation is not a class you should miss. So do your assignments and prepare for the next lecture. Thank you for listening. Thank you for your audience, and thank you for being here. Catch you later. Bye.
Someone asked a question, do you believe in this miracle? How do you open blind eyes?